this is attracted by this, automatically this will be attracted because south pole of the rotor is attracted by north pole of the stator of the blue phase. Correct? Here it is phase 2. It is same, you can understand. Similarly, this is attracted, south pole of the stator, blue phase stator, attracts the north pole of the rotor, which is a permanent magnet. That means this will rotate, torque is produced. Big attraction force, we call it a torque. That means it will align like. Correct? You can let me clear this, you will see that. This, after some time, the rotor will be attracted. This is north pole, this is south pole, this is south pole, this is north pole. Because at the time instant, correct? In the particular time instant, this has become south pole because peak maximum, this one, flux is there. Correct? 5 Bu, this is maximum. So it aligns. Afterwards, you can see that next, the blue phase, in case this is red, correct? Actually, this is what there is shown a blue, instead of red, you can imagine, correct? And so after the, so there's no need to go back here. We can use this itself. So this is the blue phase. I call it as phase 1. This is the red, and this is the green. Correct? I call the phase 1. No confusion. Please remember. So this is the north pole. This is the south pole of the rotor. Correct? Arrowhead. Correct? So when blue phase is in peaking, the rotor may be something like this. It may previously, before this one, it may be like this. It was attracted by this because this is south pole and this is north pole. So this rotated like this so many degrees and aligns. Correct? The rotor aligns. Once aligns, you can tell that this is a north, south, this is south, north. So it stays at this instant. After some time, you can see the red phase become, correct, maximum this one. But this is not a step, but is continuously varying. For understanding purpose, actually, as this is decreasing, this is increasing. Correct? From peak, it is decreasing. This is increasing. At this point, at this time, you can see both are equal. Correct? Both are equal, but this is a negative. And after that, this is start increasing. Okay? If you draw the resultant vector to every time instant or every phase angle, correct? So always one phase will be the maximum voltage, maximum current, this one, compared to other two. Accordingly, that phase will be attracting the rotor, which is free to rotate. It is a permanent magnet. So at this instance, you can see here, this is what the second phase. Second phase, the red phase become maximum voltage. Okay. You can see that at this instant, the blue will become this much only, and the green is still negative, correct? Green is negative, blue is positive, but less voltage, but red has become maximum. Previously here, blue was there. So automatically, what will happen? This is south pole, this is north pole, this is north pole, south pole. So this has been attracted by from here, it has rotated. You can see that this is rotated from here to this angle. So many degrees rotated, 120 degrees rotated. It aligns and stops. But please note that it doesn't, this actually it is moving continuously. From here, this was moving like the continuously moving. If you draw the resultant magnetic field of all three, you will see that it is happening. But for understanding purpose, I shown 5 time instances. Which time instant? 1 time instant, 2, 3, 4, 5. Correct? Or I can extend to 6 also. Correct? So first time instant, the blue phase was maximum, this one. So it attracted this magnet align, rotor align. At this time instant, the red phase is the maximum field strength. So it has attracted this, rotor is rotated this one. Next, green phase. From here, this is rotated this one. So you can see that now it has originally somewhere it rotated this much, rotated this much, rotated. After 3 peaking, the rotor, which was like this, is come to a new position. Correct? So it was something like this. Understanding purpose, we can say that it was like this. Now it has rotated this much degree, and this much degree. All 3 phases. Again, you can see that again blue phase is peaking. Correct? From blue, again the rotor from here is moved to this many degree. Next, again red phase. So you can see that continuously, because the AC voltage, which is sinusoidal in nature, all three are equal strength, but they are separated by 120 degree. And the magnetic field, the resultant magnetic field which attracts the rotor, correct, is passing from one pole to one pole, next pole, next pole, like this, correct? So by the time you will see that within the 2 cycles, the rotor would have rotated 360 degree. Correct? So this is how the rotating wing. So what we say is how it works. You have a AC magnetic field. In fact, I call AC rotating magnetic field. No, correct? Generated by AC rotating magnetic field generated by stator coil. Stator coils. There are 3 coils because of AC voltage applied. Applied to stator coil. AC will apply. So AC current flows. So AC magnetic field is which is also increasing, decreasing. Because of that, the rotor. So what it does is initially the rotor was like this. I told you, maybe somewhere before you apply the voltage, the rotor can be any position. For example, it was like this. Correct? No, you have not applied any voltage to stator and rotor. Okay, rotor applied voltage. This is north pole, south pole. And you are not applied AC voltage. Once applied the AC voltage T equals 0 time, the peak, the voltage start increasing. This also increasing. This also, everything is varying. But at the time instant, the blue has the maximum understanding purpose. So this are pulled, and it align with this at this time instant. And after this one, since you can see that the red phase is increasing, it crosses blue. The maximum voltage is resultant magnetic voltage, red phase maximum. It reaches maximum at this time instant. So this is pulled and the rotor aligns like this. Rotor align in second instant. And third is, that means for phase 2, when it is maximum voltage is there, rotor is like this. When phase 1 is like this, rotor is like this. Correct? Rotor is like this for this phase, this one. And but please note that it is continuous, not the step. It is varying. This voltage is decreasing. This is increasing. As a resultant voltage at this time instant, if you consider the phase 2 become maximum, rotor has rotated so many degrees and aligned like this. Then green phase again rotated from here, it aligns. So when I give 2 rotations, automatically my rotor has rotated 360 degree. So how it is? This is the rotating magnetic field attracts the rotor, okay, north and south poles, which is a permanent magnet. You know that north pole attracts south pole, correct? So, south pole attracts north pole. So the magnetic field get locked. We say that initially, synchronous motor, when you give the voltage, AC voltage through 3 phase and rotor with the DC voltage, it may be somewhere, correct? The rotor can be somewhere like this also, middle position also. Okay, but first thing is it has to get locked with this, correct? So when this voltage give maximum voltage, correct? Phase blue phase become phase 1 become maximum. That time you have to make the rotor to rotate and get locked, correct? That is called a magnetic locking. In synchronous motor, if you give just to give 3 phase voltage to stator and a DC voltage to rotor, the motor will not run. It will not start. In synchronous motor, one of the issue is starting. Correct? Starting synchronous motor, I can say the sync motor, requires external motor. One more motor. The another small motor will be attached to the rotor of the synchronous motor. And at that time, the load will be disconnected. For example, you have a 3-phase synchronous motor and it is connected to load, right? And if you give the 3-phase voltage and a single phase DC voltage here, correct? Single phase DC voltage here to rotor, and this is for stator, the motor will not rotate because first time is it has to get magnetically locked. You have to lock it. Physically, you have to rotate this rotor so that its magnetic field comes closer to the stator magnetic field. and get locked. Okay, so that means you will attach a small motor which is called a starting motor. In synchronous motor, you need a small starting motor which will rotate the rotor so that the rotor magnetic field, north and south pole, will be get locked with one of the phases, whichever is P condition. So that way, once it get locked, then your starter motor can be disconnected. Maybe you have a clutch, you disconnect it. After that, the rotor is locked. So with rotating magnetic field, the rotor also start rotating. Starting alone you have to do. This is one of the drawback of synchronous motor, but synchronous motors are still used. They have advantages. Okay, so you understand this? Any doubt? Because this is understanding very important. Otherwise, you won't understand including induction motor. Correct? So now, what is the speed at which the motor will run? That depends upon what you call the synchronous speed of the motor, which is called as NS. Note down. Synchronous speed of the rotating magnetic, synchronous speed of rotating magnetic field. Note down. We are giving three phase because of that synchronous. So three, what is that is represent N represents speed, sub C represents synchronous speed. NS equal to 60 into F by P. Okay, radians per second or 120. Correct? We can say that 120 F by P. Okay, so you know the rotation speed can be mentioned in terms of radians per second, correct, or cycles per second. Okay, 60 F divided by P, where F equal to frequency of the power supply, frequency of AC power supply. To AC is given to stator winding. For clarity I am writing, AC voltage given to stator winding. In India, it is 50 hertz. You know that power TNEB, Tamil Nadu throughout India, electrical grid. That frequency, if you give the voltage to the synchronous motor, F should be taken as 50 hertz. Okay. Then P is the number of poles. P equal to number of poles. Okay. 60 is a constant. Correct. You can write 60 F by P or 120 F by P. Okay. So you can use any one of this formula. Okay. Okay. Yeah. Before, what is that means? You can see that this formula I write capital P. Here I written small p. Correct? The capital P represents pole pair. Correct? How many pole pairs are here? This is one pole, red pole, this is another. Together it is one pole pair. Capital P, 1P. And again I have second. Another one capital P. Then this is the third capital P. That means pole pair means I have 6 poles, because we know that opposite pole pieces are wound using same coil and same voltage is applied. In the previous slide I showed, correct? You can see that R phase is given, the voltage goes through this coil and come back and close this and ends up. So together this is small p, this is small p. Okay, together they become capital. Pole pair means 2, pair means 2. So if I want to compute the synchronous speed of the motor, I can use 2 formulae. 60 F by capital P is nothing but this, we have to 60 into 50 in India, correct? My speed, NS, rotating magnetic speed of the synchronous speed of the magnetic field, not the motor speed. Okay, divided by 3, correct? Pole pair, 3 pair, correct? Going to be 0, correct? So this is going to be 1000 RPM. The motor speed will be 1000 RPM. NS. Sorry, not motor. Rotating magnetic field speed. Correct? Rotating magnetic speed, NS, synchronous speed, which is called a synchronous speed of the magnetic field, be 1000 RPM. Instead of that, I can say that NS equal to 120 multiplied by 50 divided by 6. Correct? So, because I am talking in terms of number of poles. Number of poles are 6. 1, 2, 3, 4, 5, 6. Or Again, this is also going to yield only 1000 RPM. Correct? So synchronous speed of the rotating magnetic field can be computed with this formula. Okay. Okay. Now that I said we talked about how the synchronous magnetic field is created, which is very, very important for the AC motor working. Whether induction motor, all this thing work in the same principle. So the rotating magnet is created by supplying the AC voltage to three-phase coil, which are separated by 120 degree apart physically inside the motor. Correct? They are shifted by 120. You can see the poles. Correct? These poles are shifted by 120 degree. Pole pair if you see. Okay. So voltage current also apply. So the rotating field is created. The rotating magnetic field get locked with the rotor gets locked with rotating magnetic field, which is invisible. Please note that magnetic field invisible. So automatically the magnetic field, rotating magnetic field from each phase pulls the rotor like this, and so the rotor rotates. So torque is created. The force is created by the interaction between attractive force between pole magnet and the rotor magnets. Okay. So to calculate the torque generated in the motor, we need to understand how the synchronous motor works. So here, this figure, please take the figure, very important. Here I am shown a diagram. The red one marked with this is nothing but stator magnetic field. Correct? Stator magnetic field, which is the body in the, it is at a put, the coil is put on the stator, which is nothing but body internally. Correct? You have grooves. I will show in the next class something physical motor. There will be a lot of slots in the something like this, in which the coil will be put. Grooves will be there. Correct? Laminated grooves in which three phase will be throughout the body. Correct? And which alternate will be, this will be red phase, this will be blue phase, green phase. Again, red, green, blue. The wires will be, coil will be inserted so that when voltage is given, the rotating magnetic field, you can see that I have drawn the direction of rotation. That means the magnetic field is rotating like this. Okay. Oh, fine. So and I given the rotating speed of the magnetic field ns, capital Ns. Some books they put small ns also the same. Okay. Now there are two magnetic field. One is called stator magnetic field. The magnetic field at given instant, take one instant. At this instant, you can see that magnetic field is represented by green color. Correct? So the line I am drawing, this is the magnetic axis of the stator field at given particular instant, but it is not going to be constant. For understanding purpose, you need to, in exam, you are expected to draw this diagram. Okay. Then at the time instant, the rotor, correct? My rotor magnetic field is this. Again, I'm drawing, you can see that this is the center of the rotor. This is black color circle is rotor, and this is my direction of the magnetic field at that instant. Correct? We generally represent magnetic is a vector. Correct? So this is my stator field. This is my rotor field. Correct? Rotor magnetic field represented by F subscript R. Correct? Rotor. This is F S. Okay. Now we can see that between these two fields there is a angle. Correct? Because 360 degree. This is called as lambda. This is called a lambda. Correct? Lambda is the angle between the rotor and stator magnetic field at particular instant. Okay. Now, because there are two magnetic field, because of both are interacting, there will be resultant magnetic field, which is shown in another gray color. You can see that. This is the resultant magnetic field between the stator magnetic field and the rotor magnetic field. This angle is called as lambda. Correct? The lambda is the angle between rotor and stator magnetic fields. Okay. Now, this angle between the resultant magnetic field, correct, and the rotor magnetic field, this is called as delta R. correct? This angle. Similarly, the angle between the stator magnetic field and the resultant is called a delta S. Correct? They are called as delta R and delta S. The total angle is called phi. The total angle is called as phi. Okay. Now, due to now that, as I told in the previously, once we apply this one, the stator is correct. Stator magnetic field is phi lambda angles away. Correct? Lambda angle. This is lambda angle. This is away. But it should move and get locked with this north and south pole. Please see that north pole of the stator is on left side. South pole of the stator in right side. The magnetic axis is like this. Again, here the north pole of the stator is here. South pole of magnetic, the magnetic axis is this. The resultant magnetic field is this. Because of this, correct, the magnetic field of the stator attracts the rotor, correct, which is aligned like this, and correct, attracts towards this, correct. So similarly, this side also it is attract. Then this south pole of the rotor is attracted north pole of the stator, and north pole of the rotor is attracted by south. So finally the rotor should align something like this, correct. South here, north here. That means this has to move, correct. So you can take this figure. This figure you have to draw in the exam. Expected to draw this and explain how it works. So we know that resultant field, magnetic field Fr, and rotor field called Fr, small capital Fr. Capital Fr is resultant, small r represent rotor, and small Fs is the stator. Now that you know that. Now, when I give initially, when the power is given, as I told you, due to the inertia of the rotor cannot go and catch atom on its own. Correct? Rotor has a mass. Correct? Please note that rotor has a mass. Correct? It has a mass, and the mass will not allow the magnetic flux field of the stator is not sufficient to attract this one and pull it. So that means you have to rotate this one, align like this. We need to align the rotor using external this one by attaching one more starter motor. Okay, and rotate it physically, so you just get locked. Then once it is locked, then you can disconnect this. That's what is mentioned here. Okay, non-self starting, because of this only synchronous motor cannot start this on its own. By using an auxiliary motor, rotor is run to close to the synchronous speed of both the field. That means we know the synchronous speed. How will you find out? Synchronous speed ns equal to 120 F divided by P, or ns equal to 120 F divided by small p or capital P. And you know that depends upon number of rotors, all those things in the given problem. Then you have to rotate your rotor initially, so that it just get locked with the rotating magnetic field, north and south pole, align like this. Okay, so north and south, they can rotate together. Okay, so this is south, this is north. Okay, any doubt in this? I just want to complete this, and so that we can. I know that it is, yeah.
No issue, sir.
Okay, sir.
Okay, so figure you want to see. Shall I go to the next slide?
Yes, sir.
I think you would have noted this figure also. In the exam, you are expected if the question is asked. These two figures are important figure. Now we know that in synchronous motor, I say sync motor, formulas are important, note down. Synchronous speed of rotating magnetic field. Represented by Ns equal to, already you know that, 60 F divided by capital P, or 120, extremely sorry. (120 F divided by small p, where P is called pole pair, small p is called as poles, number of poles. In the exam, if you are given, say, 8 poles, I am not going to give 8, correct? So 12 poles, correct? 6 poles, correct? Then you have to use this. And if you want to use that, the number of poles, I say 12 poles divided by 2 is giving pole pair, that should be substituted here. If I give 6 poles, it should be divided by 2, this will become 3, and this will become 6. So if you use wrong formula, you will get wrong speed after the, because you are going to do other calculation based on NS. Everything will become wrong, then you will get 0 mark. Careful. Okay. So we know you can use any one of that, but you should know what it is. Read the question, then you will understand. Okay. So now F is the supply frequency. In that already we know that F is called as supply frequency. In India, generally we say 50 hertz or 50. Supply frequency F equal to 50. Okay. Now, main important characteristics of synchronous motor. One is the synchronous motor. Synchronous motor, we are talking AC synchronous motor, will run either at sync speed or close to sync speed. We will say why it is later. Close sync speed. Sync speed means the magnetic field is rotating. Its speed already we calculated 120 F divided by small p, or 60 F by capital P, and you have calculated 6p, already say 1000 RPM, correct? That is magnetic field rotation. The rotor speed, which is called motor speed, can be maximum of 1000 RPM. It cannot be more than that. But many times it will be slightly less, correct? Rotor speed or motor speed, both are same. Rotor is nothing but on which you are going to connect rotor. Its speed will be always lesser than the synchronous speed, because of there's a time lag, correct? Catching up at the maximum speed. Maximum speed will be rotor speed and synchronous speed and rotor speed. NS is called as synchronous speed. NR is called as motor speed. Some books they call it NM, correct? These two will be equal when no load condition, very less friction, correct? And small motors, and that also the inertia of the motor is less, correct? The mass of the rotor decides, and also the less friction, good bearings, all those things. NS can be NR, that is called rotor or motor speed. That also very this one speed. But many times NS will be greater than NR. Not too much. It can be few RPM, correct? So we say the synchronous motor will run either at sync speed or close to sync speed. It cannot be run at any other speed. You cannot run the motor at 500 RPM, 600 RPM by varying voltage, current, whatever you do, it cannot be changed. So synchronous motor will run close to NS, no load condition, and loaded condition slightly less, but only. So generally what they say in books, synchronous motor will run only at sync speed, correct? Otherwise it won't run. Only at that is very important. It is a constant speed motor. It is a constant speed motor. 3. This constant speed, the speed depends upon frequency supply and the number of poles. In the equation, see, we know that speed generally close to ns, which is called synchronous speed, rotating magnetic speed. The formula clearly states, correct, 120 f divided by small p, correct. So where the p is number of poles and f is the supply frequency. Once this is fixed, in India it is 50 hertz. You go to US, in India 50. Go to US, it is 60. You go to France, it is 70. Correct? Japan, something else. Most of the Commonwealth countries, British ruled countries except US. Correct? All other countries are following 50 hertz. Around 20 to 30 countries. Correct? And US follows 60, and few other South American country, they buy equipment, motor, all the USA, because they did not industrial this one for last 100. Now they are caught up. So they are also adopting 60. Few of the countries. And France uses 70 hertz. The supply frequency France is 70 hertz. Okay. So that means the F will be fixed in the world. Correct. Only the any one 50, 60, or 70. And P number of poles. It can be 6 or 12, something like that. Depends on what is speed you want. You decide what is speed you want for given this one. Accordingly, poles also you can, while design what you design. So it runs at the constant speed only. Correct. It is not self-starting. It cannot start itself. You give the stator with 3-phase, rotor with a DC voltage, motor will not run. What you have to do? You have to put additional mechanically coupled. The rotor will be coupled to a small motor we call starter motor, and you have to run the motor such that the motor, which is starting motor speed, is same as synchronous speed. We said 1000, correct? Synchronous with 1000. That means rotor should be rotated. By giving DC voltage, in addition, you have to make the rotor to rotate at 1000 RPM. And when you are doing, at some instant, automatically, the rotor will be magnetically locked to the magnetic field stator. After that, you can disconnect the starter motor. And then you can connect your load. The motor will be able to take and maintain the constant, not self-starting. So you need additional this one. Then the last one is it can work on leading or lagging power factor. Okay. So it can work. These are the main important characteristics of the motor. And I stop here. Tomorrow we will continue the other. Excuse me. Tomorrow we'll continue about the torque equation and the phasor diagrams and the speed, torque, curve, power curves, and other important types. There are 2 types of how they are working. What is the difference? One is called salient pole motor. Other one is called non-salient pole synchronous motor. Those difference we'll see. After that, we'll start in the induction motor. Okay. Tomorrow I'll complete first of this. Next we'll start our induction motor. Thank you.
Thank you, Mr.
Thank you. Kind of you. Have a nice day.
Thank you, sir. Thank you, sir.
Give your attendance without forgetting. Important. That is important.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.